In this module, we discuss pharmaceutical environments. To be more precise, controlled environments for drugs and devices. Both users and designers have had very little reference material for designing such, executing such environments. If at all there was any reference, it pertained mainly to sterile processes, environments for aseptic processing. But very little was available for non-sterile formulations. About 10 years ago, ASHRAE came up in their revised edition, devoting an entire chapter to pharmaceutical HVAC. Now, in 2006, with the increase in high potency formulations, high potency drug substances, cytotoxic drug substances, WHO came up with a technical report 937, which in its Annexure 2 discusses the kind of environment they'd like to see for non-sterile solid dosage forms. The focus earlier had been purely on contamination exclusion and cross-contamination prevention. But in this report, WHO has gone beyond contamination exclusion to contaminant containment. The focus shifted to containment facilities because of the nature of the drug substances and drug products. EU GGMP and other regulators had always maintained the guide is not intended to cover security aspects for the personnel engaged in manufacture. This may be particularly important in the manufacture of certain medicinal products, such as highly active, biological, and radioactive medicinal products. But they are governed by other provisions of community or national law. But in its 40th report, WHO states these guidelines focus primarily on the design and good manufacturing practices, requirements for HVAC systems for facilities for the manufacture of solid dosage forms. Most of the system design principles for facilities manufacturing solid dosage forms also apply to other facilities such as those manufacturing liquids, creams and ointments. These guidelines do not cover requirements for manufacturing sites for the production of sterile pharmaceutical products. Areas for the manufacture of pharmaceuticals where pharmaceutical starting materials and products, utensils and equipment are exposed to the environment should be classified as clean areas. So on the one side we have contaminant exclusion and on the other side we have contaminant containment to protect both the operators as well as the environment, and the totality of these schemes comes under the general heading of controlled environments. Now I request those of you who are HVAC veterans to bear with me while I explain in the simplest possible terms the difference between conventional air conditioning and controlled environment air conditioning. If we speak about air conditioning a cinema theatre, a restaurant or an office, the focus predominantly is the comfort of the people in the room, the temperature uniformity and the humidity control. A certain amount of fresh air is required to prevent the room air from getting stale. The air changes that are designed range from 2 to 6 air changes per hour, and all the air that enters the room is taken out and tempered and returned to the room. Any bleeding that occurs is made up with fresh air drawn from outside and properly treated and tempered and mixed with the room air and returned to the room. In the case of the controlled environments, the requirements go far beyond just temperature and humidity. Temperature is certainly very important, humidity too is very important. But there are other parameters. The incoming air quality, the cleanliness, so the bioburden as well as the particulate burden in the air becomes the center of focus. Apart from this, there would be requirements of maintaining overpressures or, in some cases, underpressures with respect to the surroundings. So the delta P, or the pressure gradient or pressure differential, is also an important issue. You could add to this, depending on the application, control on noise, control on vibration, and energy savings. In controlled environments, the number of air changes is far beyond 2 to 6 that suffices for comfort cooling. It could be, in some cases, 10 air changes, 15 air changes, 20 air changes, 30 air changes, 50 air changes, and can go up to 700 air changes, depending on the application's requirements. Now, with such a high amount of air dilution, all the air from the room is not returned for retreatment, retempering. If that were to happen, you would freeze up. So, certain amount bleeds out because of your overpressure designs or underpressure designs. Part of it or all of it may be exhausted out depending on the application. Some very small fraction is returned for tempering if there is recirculation allowed, and the bulk of it is returned directly for refiltration. Fresh air to make up for the air lost is drawn in and tempered and mixed with the rest of the air and returned to the room. Now the fresh air could be 10%, 15%, 30%, and in some rare cases, 100%. In air conditioning parlance, they refer to something called the high end of HVAC, which takes care of the tempering, and the low end of the HVAC, which refers to the air distribution. Now let us see what all comes under the high end and what all comes under the low end of HVAC. In the high side, the air tempering system, you have the refrigeration system itself, the condensers, the evaporators, humidifiers, compressors, chillers, heat exchangers, and the mixing valves. On the low side, you have the air handling unit, the booster blowers, the return air ducting, the exhaust air system, the filtration system, the supply air ducting, and the fresh air system. ASHRAE had given some very interesting tips for pharmaceutical environments, and let's see what they say. Mark of a good design lies in its ability to control these parameters with due regard to industrial engineering, energy conservation, safety aspects, at reasonable installation, operation, and maintenance costs. HVAC system design influences architectural layouts with regard to items such as airlock positions, doorways, and lobbies. The architectural components have an effect on room pressure differential cascades and cross-contamination control. The prevention of contamination and cross-contamination is an essential design consideration of the HVAC system. In view of these critical aspects, the design of the HVAC system should be considered at the concept design stage of a pharmaceutical manufacturing plant. Good design practice requires careful assessment of the facility requirements and involvement at the conceptual stage itself, knowledgeable and experienced representatives from design, construction, commissioning, qualification, operations, production and maintenance, which is one motivation behind the clause as agreed between buyer and vendor that the ISO documents are so full of. It is particularly important to set target values, variance limits and the criteria for acceptance for each parameter. A design that considers such maintainability concerns as accessibility for cleaning, testing and repairs, frequency of maintenance and availability of spare parts as important requirements is likely to prove much more reliable in operation. Failure of HVAC can compromise the process. The achievement of a particular clean area classification depends on a number of criteria that should be addressed at the design and qualification stages. A suitable balance between the different criteria will be required in order to create an efficient clean area. Some of the basic criteria to be considered while designing should include outside air conditions, building finishes and structure, type of product and process, the process being carried out, occupancy, personnel flow, material flow, equipment movement, air filtration, air flow direction, air change rate or flushing rate, room pressure, location of air terminals, air cleanliness, temperature and any other parameter, and finally